Now let's look at multiplying and dividing radical expressions. If I'm taking the nth root of a and the nth root of b, and they're both real numbers, then the nth root of a times the nth root of b is equal to the nth root of a times b. So basically what I'm saying is you can take this radical and extend it above the product. Similarly, if you're doing division, the nth root of a divided by the nth root of b is the nth root of the quotient. So the quotient of the radical is the radical of the quotients. So let's look at this problem right here. When you look at this problem, I'm taking the cubed root of 6 and the square root of 2. There's nothing I can do with this. So this is the simplest you can write this exactly. Suppose I want the cubed root of -4 times the cubed root of 2. This I can move under one radical. So I'm going to rewrite this as a cubed root of -8, which is the cubed root of -2 cubed, which is -2. Yes, you could have just written -2 from here, but I'm going to show all the steps. Now, what if I wanted the cubed root of 54x to the 5th? Well, I'm going to come over here and let me look to see, hold on, I'm going to do it this way. This is the cubed root of 54 times the cubed root of x to the 5th. So let's break these up separately. 54 is what? Well, it's, let's see, 27 times 2. And that is the cubed root of 3 cubed times 2, which is a cubed root of 2 times 3. So I'm able to factor the 3 out. Now I'm going to come back and do the same thing with my x to the 5th. This is x cubed times x squared. The cubed root of x cubed is just x. And this is a cubed root of x squared. So when I rewrite this, I broke them up, and now I'm going to recombine them. So this is 3x. I'm going to pull my constant terms out. The cubed root of 2x squared. We could have done this really all in one step. You didn't have to break it up into that much detail. You could have written the cubed root of 54 x to the 5th as the cubed root of 3 cubed times 2 times x cubed times x squared. This probably would have been an easier way to do it. So this is a cubed root of 3 cubed x cubed times the cubed root of 2x squared. So this is 3x times the cubed root of 2x squared. Sometimes when I go to make things simpler, it actually makes them harder. What about something like this? I'm taking the square root of 72x cubed y squared times the square root of 10xy cubed. Well, this is going to be the square root of 72x cubed y squared times 10xy cubed. So now let me collect like terms. This is going to be the square root of 720 x to the 4th, y to the 5th. Now, the 720 can be rewritten. You could take it down to its primes, but it is 144 times 5. Now I'm doing this because I know 144 is 12 squared. And then this is x to the 4th y to the 5th. So this is the square root of 12 squared times 5. And I'm going to write this as x squared squared. That's what x to the 4th is. And y to the 5th is y squared squared times y. So this is the square root of 12 squared. And pull out the ones that I've been able to square. X squared squared, y squared squared. And what I'm going to leave in this leftover radical, the square root of 5y. The square root of 12 squared is 12. The square root of x squared squared is x squared. And the square root of y squared squared is y squared. I don't need any absolute values because they're squared, so they're, of course, going to be positive. Now, what do you do when you have this division? Well, I'm just going to take this radical and make it over the whole thing. You always want to simplify as much as you can first. All right, so this is going to be the square root. 18 divided by 2 is 9. And this is going to be x to the 5th divided by x cubed. Let me show you a way to do this. We're going to learn another way in a bit. So x to the 5th is x cubed times x squared all over x cubed. Now this radical does extend down here. Now these x cubes cancel. So I'm left with the square root of 9x squared. So the square root of 9 is 3. The square root of x squared is the absolute value of x. Now what do you do when you have this cubed root? This can be a little bit ugly. The first thing I'm going to do is I'm going to extend the cubed root over the quotient. This is 162 y to the 5th divided by 3y squared. Now, pen's working. 162 divided by 3 is 54. And y to the 5th, I'm going to write this as y squared times y cubed. And this is over y squared. So the y squares are going to cancel. My pen is acting up, I'm sorry. So this is a cubed root of 54 y cubed. So let's rewrite 54. This is a cubed root of 54 is 3 cubed times 2 times y cubed. So this is a cubed root of 3 cubed y cubed times the cubed root of 2, which is 3y times the cubed root of 2. Now, sometimes you're going to need to do what we're going to call rationalizing the denominator. The first thing you're going to do in a problem like this is simplify it as much as you can. 5 and 12, nothing simplifies. I have x squared in the numerator, y squared in the denominator, and z in the denominator. So nothing's going to simplify. So I have to do something. Let's start with taking this cubed root and putting it over the numerator. I lost my 5 there. And then over my denominator. Well, let me take everything in the denominator down to its primes. So this is a cubed root of 5x squared divided by the cubed root of, now you remember how to do your primes? 12 is 4 times 3, which is 2 times 2 times 3. So this is 2 squared times 3 times y squared times z, and we're going to extend that. Now we want to get this cubed root out of the denominator. In order to get the cube out of the denominator, I've got to have everything in here be able to be raised to the power of 3. So we're going to have to rationalize the denominator, and this is kind of a trick. We're going to keep the same root. All right, it was a cubed root. Now, I have everything down to their primes. I have 2 squared. I need one more 2 to get this to be 2 cubed. I have 3. I need 2 more 3's, because that's related to 1, to get this to be 3 cubed. I have y squared. I need one more y to get this to be y cubed. And I have z to the first power. I need I need 2 more z's to get this to be z cubed. So what I do to the denominator, I must do to the numerator. 2 times 3 squared y z squared. Now watch what happens when I combine these. Let me switch my pink color since we're merging. This is going to be the cubed root of, now I'm going to move everything in the numerator underneath the radical. 5x squared times 2 times 3 squared times y z squared. We're going to clean that up here in a minute. Now this is the cubed root of. If we did this right, it should simplify. I'm going to have 2 squared 3y squared z, and that's going to be times 3 times 3 squared times y times z squared. Ugh. All right, let's collect terms and see if we can simplify this at all. This is going to be the cubed root of, I have 5 times 2 is 10, times 3 is 30. Oh, hold on, let me undo that. Messed up. It's 5 times 2 is 10 times 3 squared, so times 9 is 90. I have x squared and no other x terms, so x squared. I have 1y and 1z, or excuse me, 2 z's. So I've simplified the numerator as much as I can. Now, let's go to the denominator. This is a cubed root of. I have 2 squared and 1 2, so this is 2 cubed. I have 1 3 squared, so this is 3 cubed. Y squared, y cubed. Z times z squared is z cubed. So you see in the denominator, I'm taking the cubed root of a bunch of things that are cubed. So this is a cubed root of 90 x squared y z squared divided by 2 times 3 times y times z. Don't know why that didn't write. One more simplification. This is the cubed root of, come on, pen, 90 x squared y z squared. I think my pen is tired of this problem. 6 y z. Now I want to point out something. This has been factors as much as it can be. If you look, the highest power of each of the terms in the numerator is less than the root, so we're good to go.